Hi everyone and welcome to another topic. Today we're going to be learning about the De-Moivre'S Theorem. Today is another section of complex numbers. This is a unique section. There will be a lot to learn in this one, I encourage you. So just sit back and let's learn something new. Alright, so the De-Moivre'S Theorem. So the De-Moivre'S Theorem, it states that for real values of n, for a complex number in polar form, we can raise the complex number by a power of n using the formula shown below. So this is the formula that we're actually shown. Alright, so this is the formula that we're actually shown. So z power n is equal to r power n cos n theta plus I sine n theta. Now this actually reminds me of the polar form that we've actually just dealt with in the former video. But alright, let's see how we come up with the De-Moivre'S theorem. So what I'm going to be showing you is two different ways you can express it. So one of the ways there will be an r, and in the other there will be no r, but they're actually basically the same thing. So let's see how we come up with the De-Moivre'S theorem. Now if you're given, remember from the polar form, if we're given z is equal to r, bracket cos theta plus I sine theta, we know that if we square z, squaring z is similar to having z times z. So it's similar to having this times itself again. So that's why we can actually expand it that way. So what happens is we can actually see that the r's shall multiply themselves. That's why we have r squared. Then we're left with this times that. And then if we multiply these, we can actually see that we'll have cos squared plus I sine theta cos theta plus I sine theta cos theta plus I squared sine squared theta. But remember that I squared means -1. So we're going to place that there. Then you can see that this and this shall add to give us 2I sine theta cos theta. So this is what we're left with. So now if we combine the cos squared theta minus sine squared theta, we can have this, and then we'll have this going to that side. Now remember this, that from double angles, remember this is similar to cos 2 theta. And then you can also see something here, that 2 sine theta cos theta is similar to sine 2 theta. So that's why we're left with I sine 2 theta. So these are actually similar. Alright, as you can see, something has already happened. You can actually see that if the z is squared, you can actually see that the 2 can be put in, and then we'll have something that is similar and to look like that. So let's look at it in even, let's delve deeper. Let's see what if we have z cubed. We know that z cubed can be expressed as z squared times z. And then we remember we've just found out what z squared is, so we don't need to expand that again. So we can just multiply that to z. So z squared, that would actually derive it to be equal to this, and then z represents that. So when we multiply the two, we can see that r squared times r is r cubed. Then when we have this times this is what we end up with. Then when we open those brackets, it can be expressed in this format. Then we can also see that similarly we have I squared becoming -1. Alright, so now we can actually see that we can actually combine this and this together, and then we can actually, so we're just going to separate the values that have I and the values that don't have I. So this is going to be the real part, and this is going to be the imaginary part. So we've just basically separated the two. Now we can actually see something unique happening. This is actually a format of expressing compound angles. As you can see, we have cos 2 theta cos theta minus sine 2 theta sine theta. This actually reminds me of a compound angle where we have cos 2 theta plus theta. So this is actually an expression of a compound angle. Then similarly, this also is an expression of a compound angle where we have sine 2 theta plus theta. So that's why it can be expressed this way. Then we also know that 2 theta plus theta is 3 theta, and then 2 theta plus theta is also 3 theta here. So we're left with z cubed being equal to r cubed cos 3 theta plus I sine 3 theta. Are you seeing a pattern? So when you have z cubed, you can see what happens. You have a 3 within, and then r being cubed. Alright, let's look at it one more step. Let's look at z power 4. So z power 4 can also be z cubed times z, which is equal to r cubed, which is what we found here, times r cos theta I sine theta. So now when we open those brackets, we can actually see that the r times r cubed is r power 4, and then we can see that we are left with that. And then when we open these brackets, so this can be expressed in that format. Then we also remember again that I squared is -1, so we have this as a negative. So this can become that. So we can now combine, we can also separate the I values from the, so we can separate the real values from the imaginary one. So we're also left with cos 3 theta minus cos 3 theta cos theta minus this plus I sine theta cos 3 theta plus that. So you can also see something here. This is actually an expression of a compound angle. So which compound angle? This is the compound angle cos 3 theta plus theta. Then there's also the compound angle sine 3 theta plus theta, of which we pull the I out. Then you can actually see that z power 4 can now be equal to r power 4 cos 4 theta plus I sine 4 theta. So therefore we've actually established a pattern which is actually true. So it's true that z power n is equal to r power n cos n theta plus I sine n theta. So that's how the De-Moivre's theorem comes about. So the above results show us that z squared is equal to that. So this is what we had actually found out from what we've derived, that when we square the z value we end up with that. So now let's compare this and that. Now this is what we've been coming up with through what we've been deriving before. But now, so we can say that it's true that this is equal to that. So now similarly, now I can put this square in. So similarly, this so r squared with this bracket being squared is also equal to whatever we had actually derived on the other side. So now we can also see that r values can cancel. So now this is what happens when you compare this format of expressing it to that. We can actually see that we can also cancel the r values. So similarly, it is also true that cos theta plus I sine theta, bracket them being squared, is also equal to cos 2 theta plus I sine 2 theta. So now we end up having that. So similarly, z cubed can be expressed this way. We can also see that r cubed values will cancel, and then we are also left with that. So similarly, we also have z power 4. We can also see that r power 4 values cancel, then we're also left with that. So therefore, De-Moivre's theorem states that cos theta plus I sine theta, bracket then power n, is equal to cos n theta plus I sine n theta. Alright, so now we've seen that there are two ways that we can express our De-Moivre's theorem. So De-Moivre's theorem is an essential theorem when working with complex numbers. This theorem can help us easily find the powers and roots of complex numbers in polar form. Now that is something we're going to look at in the future of this topic. But for now, let's see. As we have discovered, we can express the theorem in two formats that are the same and will be helpful from here and forward when calculating numbers. So we've seen that z power n is equal to r power n cos n theta plus I sine n theta. Or we've also seen that cos theta plus I sine theta is power n is equal to cos n theta plus I sine n theta. So both of these formats will work and will be useful. So this is basically the same thing. It's just that the other side does not have the r value on it. Alright, so now you may be asked to prove this from De-Moivre's theorem by mathematical induction. So how will we do that? So imagine now this is what we actually have. So this is our De-Moivre's theorem. So we know that cos theta plus I sine theta n is equal to cos n theta plus I sine n theta. So now basically we have to prove that n is true for some different conditions. So now for n is equal to 1, we can actually see that this is what we have. So now when n is equal to 1, we can actually see that this what we have on the left hand side will basically be equal to what is on the right hand side. So it's true for n is equal to 1. So now we're going to assume that the result holds for the general value of n being equal to k. So where there is n, we're going to substitute k, and then we can actually see that it is also true. So now this means it must be true for the next integer where n is equal to k plus 1. So we're going to substitute k plus 1 for where we have n. And then what are we left with? Now we know, now here we have k plus 1. Now on this other side, what we know is actually this power here, when we have cos theta plus I sine theta, now we're looking at this left hand side. We know that this means we have, this is the same as having this to the power k multiplying another value like this with a power 1. So we're basically adding powers, meaning that it came out of two different brackets multiplying themselves, and this is what they look like. So you can actually see that from our knowledge of De-Moivre's theorem, we can put this k in, and then we're left with that. And then we can actually see that now we can open these brackets. So when open brackets and multiply, we are left with, we come up with that, of which now we know that I squared is -1. So we are given, so it becomes that. And then right now we can actually correct our real values from, and separate them from the imaginary values. So this is what we are left. So we see something related to the compound angle. So this is a compound angle, cos k theta plus theta, and then these a compound angle where we have I outside, and then this is sine k theta plus theta. So this is what we see. But we remember that alright, now we can also see that we can pull out theta. So when you pull out theta from these brackets, we are left with that. So this is, so when you pull out theta or factorize it out, we are left with that. And then we can actually see that therefore cos theta plus I sine theta into power k plus 1 is equal to that. So you actually see that it is actually true for k is k plus 1. So it's the way we've assumed that it is true. So now for n is equal to 2, we can actually see that if n is equal to 2, it also means that k plus 1 is equal to 2, because n represents k plus 1. So that means k is equal to 1. So now we're going to substitute it there. So now we can also see that we'll end up with something like that. So it is actually true, because now it means here we can put the 2 in, and then we are left with that. Since it is true for n is equal to 1, n is equal to 2, and so on, it's true for all positive integrals of n. So that's how we prove it by mathematical induction. Alright, so let's look at some important questions that will help us understand what we've actually just discussed. So being asked to express 1 minus I root 3 power 4 or bracket root power 4 in the form a plus bi. Now this is slightly a different kind of number, because now we're dealing powers that go up to power 4. So what do we do here? So solution is we're going to first express this in polar form. Is we're going to let z be equal to 1 minus I root 3. Then that means that r or the modulus is going to be equal to root of 1 squared plus we're going to have negative root 3 squared, and then we end up having root 4, which is equal to 2. So that's going to be the value of r, or the modulus. Now we can actually say that r is equal to 2. So now how do we find the argument? Now we know that this is going to be an example of a number which fits in the fourth quadrant. And why is that? It's because you can actually see that we have a positive real and we have a negative imaginary. So now we're going to place this in the fourth quadrant of the Argand diagram. Then in the fourth quadrant, you can actually see that to find the formula of finding argument of z is going to be equal to negative tan inverse of root 3 over 1, which is going to be equal to negative 60. Now the reason it's a negative is because we are going to be doing clockwise rotations, and then we're going to end up with negative 60. But now theta, which is negative 60, can also be expressed as in radians form as pi over 3, negative pi over 3. We know that pi means 180, so 180 divided by 3 is 60. So it's basically the same thing. So this is negative 60 expressed in a different way. So now we know that z is equal to that from polar form. So when we substitute in the values of argument and the values of r, we end up with that. And then now we can actually we can now go back to our original. So that means, because right now we said z is equal to that, so that means this value here is the same as z to the power 4. So now we are really looking for z to the power 4. So that means z to the power 4 is equal to that. So now here we apply our knowledge of De-Moivre'S theorem. So this is the first format of De-Moivre'S theorem, where we have z power n is equal to r power n brackets, where we have these values in, and then there is a power n outside. So this is what we are left with. So 2 to the power 4 is 16, and then we are left with that. So our knowledge, from our knowledge of De-Moivre'S theorem, we also know that this 4 can be brought in. It will not change anything. So it's also true that it can actually be expressed this way. And then we can press this in our calc. So if you put your calc in radians, make sure to put your calculator in radians. We know that cos of negative 4 pi over 3 is the same as negative a half. And then sine of negative 4 pi over 3 is root 3 over 2. So I root 3 over 2 actually. So this is what we're left with. So when we multiply the 6 within, we're left with negative 8 plus 8 root 3 I. And hence that is how we express this complex number in the form a plus b I. Alright, let's look at another example. So now this is an example of where we have 1 over 1 minus I root 3, and then we have I minus 1 root 3 being cubed. Then we want to express that in the form a plus b I. So going to do the same thing. So we're going to first express in polar form. Alright, so we know that 1 over 1 minus I root 3 to the power 3 can also be expressed as 1 minus I root 3 to the power negative 3. Alright, so now next we're going to let z be equal to the value inside. So we're going to let z be equal to 1 minus I root 3. So this is what we're left with. So now if we find the modulus of z, this is how we do it. We know that we have root power 4 and we know that that is equal to 2. So therefore r is equal to 2. Then argument of z, we can also see that this is also going to be in the fourth quadrant of the Argand diagram. And then we can see that's why we have a negative tan inverse of root 3 over 1. So we are left with negative 60 degrees. So we can see the negative 60 is also the same as negative pi over root 3 in radians. So from polar form, we can also express it this way. So now we remember that now we are left with that. So now we know z, if we go back to the original, since this is equal to z, so we're now looking for z power negative 3, which can be expressed in this format with our knowledge of De-Moivre'S theorem. So it can be expressed in this form. Obviously 2 to the power negative 3 is the same as 1 over 8, so we're going to keep it in fraction form, and then we are left with that. So from our knowledge of De-Moivre'S theorem, again we can actually see that we can actually bring this negative 3 inside. Obviously we see when we multiply it in, we end up so the 3's will cancel here, then we're left with pi, then here the 3's also cancel and we're left with pi. And since this is a negative and this is a negative, so we're left with positive signs. So that's what it becomes. So now we know that cos pi in radians is negative 1, and then sin pi in radians is 0. So now we're left with negative 1 over 8. So this is actually a pure real number, since the imaginary part of it is equal to 0. Alright, let's look at another question. So we're being asked to express root 3 plus I in modulus argument form. And we're being told, hence find root 3 plus I to the power 10 and 1 over root 3 plus I to the power 7 in the form a plus b I. Now this is an easy one, so we're going to first express in polar form. But before we do that, we're going to first let z to be equal to root 3 plus I. So we're dealing with the same complex number, root 3 plus I. So if we find its modulus, we're going to have root 4, which is equal to 2. So therefore r is equal to 2. So to find its argument, you can actually see that since every item, so the real part is positive and the imaginary part is positive, so that means we're dealing with the first quadrant of an Argand diagram. So in the first quadrant, we find the argument z by doing tan inverse minus 1 over root 3, of which the answer is equal to 30 degrees. So theta is 30 degrees, of which we know that when you express that in radian form is the same as pi over 6. I'll remind you again that pi means 180 degrees. So 180 divided by 6 is 30. So this is how we express it in radian. So we also know from polar form that z is equal to r cos theta plus I sin theta. So we can substitute in the values of the argument and the values of r. So that's what we are left with. So now we are looking for how to express, how to deal with these two different numbers. So let's first deal with this. So remember that we expressed this root 3 plus I as z. So now we're going to find z to the power 10. So z to the power 10, we know from De-Moivre'S theorem that this is what we come up with. Alright, so now we can also see that this is what we're left with. So with our knowledge of De-Moivre'S theorem, we know we can bring this 10 inside, then it becomes that. Then we can actually say that 2 power 10 is the same as 1024. Then we know that in radians, cos 10 pi over 6 is the same is a half, and then sine 10 pi over 6 in radians is root 3 over 2. So when you multiply the 1024 inside, this is what we're left with. But 1024 divided by 2 is 512. So we're left with 512 minus 512 root 3 I. Alright, so let's deal with the second part where we have root 3 plus 1 over root 3 plus I to the power 7. So now this can be expressed in that format. So this is the same as root 3 plus I to the power negative 7. So now with our knowledge of De-Moivre'S theorem, we know that this can be expressed this way. So we're looking for z power negative 7. So it can be expressed like that using De-Moivre's theorem. So now when we bring the negative 7 in, this is what it becomes. So we're left with that. But now we know from, we've pressed this in our calculator, cos negative 7 pi over 6 is the same as negative root 3 over 2. And then sine negative 7 pi over 6 is the same as a half. So it's actually is called positive a half. So when you multiply, so we know 2 power negative 7 is 1 over 128. So when you multiply 1 over 28 in, we come up with that. And now this is going to be our answer. Let's look at a question from UNEB 2004, and this was question number 15A. So we're being told, without using tables or calculators, simplify that. So we have cos pi over 17 plus I sine pi over 17, brackets, to the power 8. And then right at the denominator, we have cos pi over 17 minus I sine pi over 17 to the power 9. So how do we simplify this using our calculator? So right now, we're not going to press our calculator. It won't be necessary. So this we know this is the number we've been given. So now if we look at the values in the denominator, we can actually say that we can express it in that format. Now what do? We want to simplify this. So now what happens is we want to express the denominator in the format that looks like the numerator. So we want to introduce a positive sign here in the middle. And we know that from our knowledge of trigonometry that when we have a negative sign, it also means that it probably means that the negative came from the values of the angle. So probably this came from I sine negative pi over 17. So this is actually exactly the same as that. But also we also know that it is okay to express a cos pi over 17 as cos negative pi over 17, because these basically mean the same thing, because a negative angle does not the cos of a negative angle is exactly the same as a cos of a positive angle. So you can also make this a negative, and this is also true. So this is basically okay. Now the reason we made this a negative is because we want the value here to be exactly similar to the value here, so we can actually apply De-Moivre's theorem. So we can actually see that we can pull out a negative 1 from here and take it out, so have this being a negative 9. So now we can actually see that now what we have here and here is now exactly similar. So now we can use our knowledge of exponentials. So now we know that this and this are now exactly similar. So now this can be the same as cos pi over 17 plus I sine pi over 17. So for our knowledge of powers, so we can actually see that we have 8 minus negative 9, which is the same as 8 plus 9. So we are left with cos pi over 17 plus I sine pi over 17 to the power 17. So now again, from our knowledge of De-Moivre's theorem, we're going to see it's okay to bring this back in to simplify that. So we end up having that. So 17's cancel, then we're left with cos pi plus I sine pi. So we know cos pi is actually equal to negative 1, and then I sine pi is equal to 0 because sine pi is 0. So we're left with that. So this is exactly equal to negative 1, and hence we've actually solved hence we've simplified the equation. So got an example from UNEB 2004, and this was question number 15A. So we're being told, using De-Moivre's theorem or otherwise, simplify that. So we have cos theta plus I sine theta, brackets cos 2 theta plus I sine 2 theta over cos pi over 2 plus I sine pi over 2. So when someone sees this at once, they may think of other formulas that we've been using in trigonometry. But this is actually a number that is easy to do if you know how to use De-Moivre's theorem. So now this is what we have, but now we know from De-Moivre's theorem that this, we can actually take out a 2 from this and make it a power. Then here also we can take out a half and make it a power. So De-Moivre's theorem makes this easy and straightforward. So this is what we end up with. So now we see that these bases are now similar, and here it's also similar. So we can actually say that this and this can now add them. So we are left with cos theta plus I sine theta being equal to 2 plus 1. So this is power 1, so we have 2 plus 1. So at the bottom we keep it as e.t. So now we're left with cos theta plus I sine theta power 3 over cos theta plus I sine theta to the power a half. So now the powers can also subtract because they actually have the similar bases. So 3 minus a half is 5 over 2. Then you can bring the 5 back in, and this is what we end up having. This is what we end up having, and hence we've actually simplified it. Let's look at question number 6, and this is question number 6. So now the most important thing here is we also want to make sure that the bases will look identical so that we can actually solve the number in an easy way. So this is what we actually have here. So first thing you can actually see is actually you can see that what we're going to do is, before we compare to the other powers, you can actually see that just by looking at this here, you can actually see that we have 2 pi over 5, then we also have at the bottom 3 pi over 5. So that means we have a 1 over 5 in similar. So what happens is, I think at the top we can pull out a 2, and then at the bottom we can also pull out a 3 with our knowledge of De-Moivre's theorem. So this can be expressed in this way also. And then now we have the bases now almost looking similar. So we have a 2 out and a 3 out. But of course, this 2 and 8 can multiply. So 2 times 8 is 16 and 3 times 3 is 9. So now we have that. Now what we're going to do is, again, we want to change this negative and make it a plus. So we can actually extract this negative, and then we're going to put it here. And then also similar, we're going to convert this pi over 5 into a negative. So we actually have something similar on both sides. So now again, we can again pull out the negative 1 from here, and we're going to have a negative 9. So now we can now do this. So we can actually see that now the bases are actually similar exactly. So we now have 16 minus negative 9, which is actually the same as 16 plus 9. So 16 plus 9 is 25. So that's what we end up having. So when we bring the 25 back inside, also from our knowledge of De-Moivre's theorem, you can actually see that this is what we end up with. And then we know that we'll end up with cos 5 pi plus I sine 5 pi, of which cos 5 pi is negative 1 and sine 5 pi is 0. So the answer is negative 1. Alright, so next we're going to see how to express a compound angle. Actually, we're going to learn how to express compound angles as a single angle using De-Moivre's theorem. So this is another important section of De-Moivre's theorem. So now, for this part, you need to be able to apply the following binomial expansion. We're going to make use of the Pascal's triangle array. The Pascal's triangle contains the values of the binomial coefficient. We're going to demonstrate it below. So now this is going to be an important section, but before we do that, let's first understand the Pascal's triangle, because it's going to be very important. So imagine we have a number like this, a plus b bracket power 0. We know that the answer here is definitely equal to 1. So how about if we have a plus b to the power 1? We also know that this is just simply going to be equal to a plus b. Right, so let's go to the next number. How about if we have a plus b being squared? Now we know that this will be a square of 2 different brackets. So when we multiply the 2 brackets, we'll end up with a squared being a squared plus 2ab plus b squared. So how about if we have it as a plus b cubed? So this is going to be similar to a cubed plus 3a squared b plus 3ab squared plus b cubed. How about if we have a plus b power 4? Now this will become a power 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b power 4. And then how about when we go to power 5? It's going to be a power 5 plus 5a power 4b plus 10a cubed plus b squared plus 10a squared b cubed plus 5ab power 4 plus b 5. Now how about a plus b power 6? This is similar to a power 6 plus 6a5b plus 5a power 4 plus b squared plus 20a cubed b cubed plus 15a squared b power 4 plus 16ab power 5 plus b squared. Now we could continue on and on to power 7, 8 and the rest, but now what we wanted to do was to establish a pattern. So now it's important to look at all these and see if there is a pattern we can actually see. Now there is actually a pattern, and now that's what we call the Pascal's triangle. Now if you look at the very first value, you can actually see that we have a binomial coefficient of 1, and that's why we have a 1 at the top of the Pascal's triangle. And then when we have a plus b power 1, we can actually say that the coefficients in front of a and b, the binomial coefficients, are 1 and 1. Then when we look at squared, we can actually see that the first binomial coefficient here is 1, which is similar to that. The second one is 2, and then the third one is 1. As you can see, there is a pattern there. And then on and on, when we move to the power 3, we can actually see that the binomial coefficient here is 1, 3, 3, 1, and that's what we have here. Then we go to power 4, we have 1, 4, 6, 4, 1, and that's what we actually have there. And then when we go to power 5, we have 1, 5, 10, 10, 5, 1. That's what we have there. Power 6 is 1, 6, 15, 20, 15, 6, 1. And that's what we actually have there. So the Pascal's triangle is going to help us out to remember the binomial coefficients at each level. So this is going to be at level 0, 1, 2, 3, 4, 5, 6. That's how we count, starting from 0 to 6 and on. But also there is also a pattern in the Pascal's triangle that can also help us to remember. So as you can see, we have 1, and then we have 1, 1. So that's like 1 plus 0 and 1 plus 0, and that's what we end up with. Now to move to the next level, we can actually see that if we actually, what we see is 1 plus 1 is 2, and then we just keep these 1 values to the sides. Then you can actually see here something also happens. So you can add this 2 plus 1 is 3, and then 2 plus 1 is 3. Then we just keep 1s on the sides. So what happens is on the sides you make sure it's 1, and then the next values you just add together. So 3 plus 1 is 4, 3 plus 3 is 6, and 3 plus 1 is 4. Then 1s on the side. So you can actually see there is a pattern. 4 plus 1 is 5, 6 plus 4 is 10, 6 plus 4 is 10, 4 plus 1 is 5. Then lastly, you can actually see that 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20, 10 plus 5 is 15, and then 5 plus 1 is 6 with 1s on the side. So there is actually a pattern we can also use like that to remember the Pascal's triangle. But generally, now this format here enables us to come up with what we call the binomial expansion. So this is what the binomial expansion will look like. So it's the formula we're going to be making use, where you see NC1 simply represents the coefficient here, the NC2 represents the coefficient here, NC3 represents the coefficient here, and on as it goes. Alright, so these are going to make more sense as we do different questions. So first question, express cos 3 theta in terms of powers of cos theta. So how do we solve such a number? So now we know from De-Moivre'S theorem that cos theta plus I sine theta to the power n can be expressed as cos n theta plus I sine n theta. So this is what we're going to do. So now we also know that when we have cos theta plus I sine theta cubed, it's also equal to cos 3 theta plus I sine 3 theta. Now we know that this is also true. Now why do we exactly choose to go with powers of 3? It's because it's at powers of 3 that we can get something that has cos 3 theta somewhere. So that's why we make n to be equal to 3, because of this value here. So this value shows us that the n we shall be using is 3. Alright, so let's continue with that. So now we have a value like this. So now we're going to apply binomial expansion right on this side. So now from binomial expansion, you know this is the formula for binomial expansion. So we're going to substitute in the values, and you can see that that's what we end up with. As you can see that it can be expressed as that. As you can see, when I put a to the power n, since now cos theta will be a and I sine theta will be equal to b. So you can actually see that we end up with cos cubed theta as the first plus that, and then we also know that now this will represent the coefficient that we should actually fix in, and then it will be expanded that way. Alright, now we would go on and on, but now when we reach the level in the binomial expansion where n becomes 3, now that is where we don't continue to find the rest of the values that have coefficients, because now from here on we can actually see that now 3 minus 3 is equal to 0. So now that's where we're going to end for this number. So now when we substitute in the values, this is what we end up with. But now we can now substitute in the coefficients. So now remember from our past course triangle, at the level where we have it being cubed, we know that the coefficients are 1, 3, 3, 1. So this is what we end up with. And now we also remember that I squared is equal to negative 1, and then I cubed is the same as negative 1 times I, which is again equal to negative I. And then now what we're going to do next is we're going to collect the real, we're going to bring the real sides together and the imaginary sides together. So now we end up having cos cubed theta minus 3 cos theta sine squared theta plus 3 cos squared theta I sine theta minus I sine cubed theta. So that's what we end up with. So now next we're going to equate the real parts. Now we're going to compare it to what we actually have here. Now remember, we want to express cos 3 theta in the values of cos theta, and you know this is exactly, so the expansion here is actually equated to this. So we can actually see that from the real parts, we can actually say that this is going to be equal to the values of the real parts, which are actually these right here. So now we're going to focus on where we have cos 3 theta. Now, in case the question had asked us to express sine 3 theta in terms of cos theta, we could have actually equated the imaginary part. So we would have focused on this because this is where we would have gotten the sine 3 theta. But because the question is focused on cos 3 theta, so focus on equating the real parts and not the imaginary parts. So when you equate the real parts, this is what we see. And then we can actually see that now, since we've been asked to convert, to express it in terms of powers of cos theta, now we can convert this sine squared theta into cos. So we know that sine squared theta is the same as 1 minus cos squared theta. So when you open those brackets, we are left with cos cubed theta minus cos theta plus 3 cos cubed theta, of which when you add the two, we know that we have 4 cos cubed theta minus 3 cos theta. So therefore, cos 3 theta is equal to 4 cos cubed theta minus 3 cos theta. And that's how you express it in terms of powers of cos theta. Alright, let's look at another example. This was a question from UNEB 2003, and this was question 12a. So it will bring us to use the De-Moivre'S theorem to express tan 5 theta in terms of powers of tan theta. So how do we do this? Now, first of all, we know that tan 5 theta is the same as sine 5 theta over cos 5 theta. So now for this question, we're going to first find what sine 5 theta is, then later on we'll find what cos 5 theta is. So let's first deal with sine 5 theta. We know from De-Moivre'S theorem that this is true, so therefore it means cos theta plus I sine theta to the power 5 is equal to cos 5 theta plus I sine 5 theta. So now with this expression, you can actually see that we have the cos 5 theta here and the I sine 5 theta here. So now we're going to focus on the sine 5 theta. But before we do that, let's generally apply the binomial expansion to this left hand side. So applying the binomial expansion to the left hand side, we know this is the formula for binomial expansion. Then when we put it in, this is what we end up with. So now this goes up to power 5, so we're going to use it up to level 5, and then this is what we have. So now substituting in the coefficients for power 5, we know the coefficients are 1, 5, 10, 10, 5, 1. So you can actually use your calculator to expand this. It would also help, but this is how we use it in Pascal's triangle. So now next we're going to collect the real parts, and then we're going to collect the imaginary parts. But before we do that, we can actually see that I squared is negative 1. I cubed is going to give us a negative I. So there we're going to have it remaining. And then we have I power 4 is actually the same as a positive 1. So I power 4 is just going to basically disappear. So actually I power 5 is the same as 1 times I, which is actually I sine 5 theta. So that's what we are left with. Alright, so next we can actually see that when we collect the real parts, so we're going to combine the real parts and the imaginary parts, and that's what we end up with. So now to find sine 5 theta, we're going to compare the imaginary parts. So this is what we're going to focus on. So now equating imaginary parts, we can actually say that I sine 5 theta is going to be equal to the values of the imaginary parts. So the imaginary parts are these ones right there. So that's what we're going to actually have. and then this is going to be equation 1. But we can actually see that the values of I can cancel. You can pull out i's and they'll cancel, and this is what we're left with. So for cos 5 theta, it's going to be as simple as simply equating the real parts, because we can find cos 5 theta from the real parts here. So we're going to have cos 5 theta being equal to these parts right there. So equating real parts, we end up with something like that. So now we're going to substitute in the values we found, the equation 1 and 2. We're going to substitute in the values of sine 5 theta and the values of cos 5 theta into our equation. So now we know tan 5 theta is going to be equal to that. So we end up having that. Now we were asked to express everything in terms of tan theta. So that means we're going to convert every value of cos and sine into tan. And how do we convert into tan? The simplest way is to divide both the numerator and denominator by cos power 5 theta. So when we do that, we can actually see that at the top we're left with 5 tan theta minus 10 tan cubed theta plus tan 5 theta over 1 minus 10 tan squared theta plus 5 tan power 4 theta. And hence that is how we express tan 5 theta in values of tan theta. Alright, so let's look at another section of De-Moivre's theorem. So how about when we ask to express a single angle into compound angles using De-Moivre's theorem? So now we will investigate finding trigonometric identities for sine power n theta and cos power n theta, where n is a positive integer. So now if z is equal to cos theta plus I sine theta, so this is what we have. If that is true, it also means that 1 over z is the same as z power negative 1. So it can be expressed that way, of course, which will mean that the value on the right hand side will also be equal to cos theta plus I sine theta to the power negative 1. So now we can see that we can bring the negative 1 inside, and that's what we'll actually have. But remember that a negative on a cos is meaningless, so we're left with cos theta. And then we can see that on the side of sine, we can actually bring out the negative, which will affect the plus sign in the middle. So we're left with negative I sine theta. So that's what we have for 1 over z. So it follows that if we have z plus 1 over z, it means we have cos theta plus I sine theta plus the value that we've actually derived as 1 over z, which is actually equal to that. So now we can actually see that this will equate to 2 cos theta. Then we also can see that z minus 1 over z is going to be equal to that, of which now we'll end up having that. And now we can see that a cos theta minus cos theta, those cancel. So we're left with I sine theta plus I sine theta, which is equal to 2I sine theta. So now these are true in this case. So also we can also see that if we have z power n, we know that it can be expressed this way. So know this knowledge from De-Moivre's theorem. So now it can bring the n inside, and we are left with that. So it also means 1 over z power n is equal to z power negative n. Of course, that becomes true. Of course, that means that it is going to be equal to cos theta plus I sine theta power negative n. Now if we bring the n inside, that's what it becomes, and then we are left with that. We can see that the negative in front of the n where there is cos means nothing, so we change that to a plus, and then the negative where there is a sign, we bring that negative outside, and it affects the plus sign in the middle, so we're left with negative I sine n theta. So now we can basically see that it means generally that z power n plus 1 over zn is equal to that, and then this means that it's also equal to 2 cos n theta. Then z power n minus 1 over z power n is equal to that, of course, which eventually will be equal to 2I sine n theta. So now we've actually come up with something that is true. So in summary, it means z plus 1 over z is equal to 2 cos theta. Of course, then z minus 1 over z is 2I sine theta. Now, this is something that is basically true for these kinds of numbers. Or, in a more general format, z power n plus 1 over zn is equal to 2 cos n theta, and then z power n minus 1 over zn is equal to 2I sine theta. Now these are cases where we have power 1 on the z. This becomes true. So this is the most basic. But then in case there is a higher power in any kind of number, where they have z power 2, power 3, power 4, power 5, and on, even a power 10. So you can basically use these. But these are basically related. Alright, so let's see how to use this in practice. So express cos power 5 theta in the form a cos 5 theta plus b cos 3 theta plus c cos theta, where a, b, and c are constants. So let's see how we can work this out. So remember that z plus 1 over z is equal to 2 cos theta. So what that means is if we put that to the power 5, we know that that will become that to the power 5. So why are we doing that to the power 5 is because there is a power 5 here. So I want to create something similar. So now we can actually see that that will be equal to 32 cos power 5 theta. So now that is going to be basically true. So now we're going to keep that there and we're going to come back to it. Now let's apply binomial expansion to the value on the left hand side. So when you apply binomial expansion, so it's the formula for binomial expansion. So when you substitute the values of a and b, of course a being z and b being 1 over z, we can actually see that this is what we end up with. So we go up to the coefficient where there is a 5. So we go on and on up to the coefficient 5 because we have a value 5 at the top. So when you substitute in the values, so you know that the coefficients from a Pascal's triangle, the coefficients of power 5 are 1, 5, 10, 10, 5, 1. So now that is what we end up with. So now next basically we can see that when we open brackets, we know that 5z power 4 times 1 over z is going to be equal to 5z cubed. 10z cubed times 1 over z squared is going to be equal to 10z. And then 10z squared times 1 over z cubed is 10 over z. Then here we have 5z times 1 over z power 4 is going to be equal to 5 over z cubed. And then 1 plus 1. Then this stays as it is actually. So now we can basically do something else. We can actually collect the values that have power 5 and the values that, so just collect like terms. So basically we are going to combine this and that. So where the powers of z are similar, we combine those values. So this is how they look when you combine the different values. So this where we have powers of 5, here is where we have powers of 3, and here we have powers of 1. So now we can factorize out in each individual group. So these are the different groups that we actually have. So now we can see in the first group we have that. Then in the second group we can actually pull out a 5. That's what we end up with. And then in the third group we can pull out a 10. So now from our general knowledge of that we've actually seen, we know that z power n plus 1 over zn is equal to 2 cos n theta. So now this is the general format and we're going to apply that knowledge here. So you can actually see that in this first part, now this is going to become 2 cos 5 theta. Then in this next second part, this is going to become 5 times 2 cos 3 theta. Then in this other side, we have 10 into 2 cos theta. So this is what we end up with. So when you open those brackets, we have 2 cos 5 theta plus 10 cos 3 theta plus 20 cos theta. So now, therefore, we can actually see that now we can equate the values that we have here. Whatever we found here, we can now equate it to the value on the right hand side. So now the value, so now this is the answer to what we have here. So now we can equate it to this value to continue solving. So therefore 32 cos 5 theta is equal to that. And then now basically I'm going to make cos power 5 theta the subject because it's what we are looking for. And then so it will become that. So therefore we can actually see that when we reduce the values on the right hand side, we know 2 over 32 is the same as 1 over 16, 10 over 32 is the same as 5 over 16, and 20 over 32 is the same as 5 over 8. And that is how it looks in the most simplified way. So if we compare this with what we had actually been given in the question, if we compare it with that, we can actually see that A is 1 over 16, B is 5 over 16, and C is 5 over 8. Alright, let's look at another question. So we're being asked, use De-Moivre'S theorem to show that cos power 6 theta is equal to what we have right there. Now this is another example, so we're going to basically use the same method. So we know that z plus 1 over z is the same as 2 cos theta. Now, why do we focus on z plus 1 over z? It's because that is the format that has a cos somewhere inside. If we're dealing with a sine value here, a sine power of any value, would actually be dealing with z minus 1 over z. But this is another example where we deal with z plus 1 over z. So now z plus 1 over z, if we put that to the power 6, is same as that. So we know that 2 to the power 6 is 64, and cos on the cos we have cos power 6 theta. So now we're going to apply the binomial expansion to the value on the left hand side. So this is the formula for binomial expansion. So we're going to expand up to power 6, and this is what we end up having. So when you substitute in the coefficients of power 6, the coefficients are 1, 6, 15, 20, 15, 6, 1, and that's what we end up having. So now when we open brackets, you can actually see that this is how it looks in the more simplified version. So now we're going to group like terms where z's have the same powers, and that's what we end up having. Now the power 20 does not group with any, the value 20, so it's just left and put on the far right side, and that's what we have. So now we can factorize out individually, so you can actually see that this is what we end up having. So we know that z power n plus 1 over zn is equal to 2 cos n theta. So with that knowledge, you can actually see that this is the same as 2 cos 6 theta, and then here we have 6 times 2 cos 4 theta, then right here we have 15 times 2 cos 2 theta plus 20, and that's what we have. So when you open those brackets, we have 2 cos 6 theta plus 12 cos 4 theta plus 30 cos 2 theta plus 20. Alright, so now therefore it means that now when we compare the different values, so now we can equate these to the value on the right hand side. So now we have this being equal to the value that we found from this expansion. So therefore we know that 64 cos 6 theta is equal to that. So now we can make cos power 6 theta the subject, and that's what it becomes. So now when we simplify this, you can actually see we would end up having cos 6 theta over 32 plus 3 cos 4 theta over 16 plus 15 cos 2 theta over 32 plus 5 over 16. And basically that's what we are being asked for in the question, and that is the proof. Alright, let's move on to another question. So sine power 4 theta in the form d cos 4 theta plus e cos 2 theta plus f, where d, e, f are constants. Now this is an example where we have a sine power 4 theta. Now for this case, we're going to use z minus 1 over z. So we know that z minus 1 over z is 2i sine theta. Now we're using this because this is the format that gives us sine theta. Alright, so now we know that if we put that to the power 4, this becomes 2i sine theta power 4. Then we put the 4 in, we know that 2 power 4 is 16. Then we have I power 4 sine power 4 theta. Alright, and that's what it is in a simplified version. It's because I power 4 is equal to 1. Alright, so now applying binomial expansion to the value on the left hand side, which is z minus 1 over z power 4, we know that this is the formula for binomial expansion. So this is how it looks when it's expanded. So now when we put in the coefficients are 1, 4, 6, 4, 1, because we're dealing with power 4, and that's what we have. So in open brackets, this is what we have in a simplified version. So now when you combine and collect different like terms where we have the same value of z squared, and then we're going to separate the 6 value to the far right, and that's what we already have. So you can actually see that there is actually now something there. So now we know that z power n plus 1 over zn is equal to 2 cos n theta. So we know that this is what it becomes. So for these values, now we have 2 cos 4 theta. Then right here, these are equal to 2 cos 2 theta times this 4 right there. So when you open those brackets, we're left with 2 cos 4 theta minus 8 cos 2 theta plus 6. So therefore, it means that now we can compare these values here, the values we found from this expansion, to the value on the right hand side. So we have 16 sine power 4 theta is equal to 2 cos 4 theta minus 8 cos 2 theta plus 6. So making sine power 4 theta the subject, that is what we are left with. So now when we reduce that, we can actually see that this is what we end up having. So now when we compare to what we were given in the question, you can see that d will be equal to 1 over 8, e shall be equal to negative a half, and f shall be 3 over 8. And that's how we solve the question. Alright, let's look at another question. So this was question number 4. So we're being given that z power n plus z power negative n is equal to 2 cos n theta. Now that is already a formula that we are familiar with. Z negative n is actually the same as 1 over zn, so it's basically something we're familiar with. So given that, solve the equation that. Now this is an example of what we call a cyclic equation. If we look at what we actually have here, now this is an example where whatever we've been learning so far in this section can actually be useful to solve and find the power of the value of z. So it's a cyclic equation, and why is that? It's because the values, if you look at it clearly, we can see that we have a 16z squared in the middle, and then we have an 11 on the right hand side and a 5 again on the other side. So it's basically a repetition, so it's actually like circular. So we have this appearing here and this appearing there. So this is how cyclic equation looks. It means that we have a middle value, which is that, and then we have this and this being similar, and then we also have that and that being similar. So this is cyclic, and that's we're going to apply the knowledge of cyclic equations. So now let's deal with that equation. So this is what we actually have. So now, it being a cyclic equation, it means we can look at the middle value here, which is 16z squared. Then we can factorize out the value we have in the where we have on the middle. So we're going to factorize out a z squared because it's a cyclic equation. So when you factorize out a z squared, we're left with 5z, inside the brackets we're left with 5z squared minus 11z plus 16 minus 11z power negative 1 plus 5z power negative 2. So now we can see that either z squared is equal to 0 or 5z squared minus 11z plus 16 minus 11z power negative 1 plus 5z power negative 2 is equal to 0. So now let's deal with this side of it. So when you compare those to being equal to 0, we can actually see that that's what we have. So now we're going to group different terms. So we're going to group the terms where there is actually powers of 2, and we're going to group terms where we have powers of 1, and then we're going to separate the 16 and bring it to the far right side. Now we're going to apply the knowledge that we've actually been using. So now this is what we actually have. Alright, now we know that from z power n plus z power negative n is equal to 2 cos n theta, which is what we already given. We can actually see that now we can apply that knowledge. We can actually see that these become 2 cos 2 theta, and then these become 2 cos theta, and that's what we end up having. So when you open those brackets, we're left with 10 cos 2 theta minus 22 cos theta plus 16 being equal to 0. So now we can actually see that now we can convert this. Now this is a double angle, so we're going to simplify it. So this is the same as 2 cos squared theta minus 1. So when you open those brackets, we have 20 cos squared theta minus 10 minus 22 cos theta plus 16 being equal to 0. So now it becomes 20 cos squared theta minus 22 cos theta plus 6 being equal to 0. It's because 16 minus 10 is 6. So we are left with a positive 6 on the far right. So now we can actually before we let it, let's first simplify this. So dividing everything by 2, this becomes 10 cos squared theta minus 11 cos theta plus 3 being equal to 0. So we're going to let x to be equal to cos theta. So we're going to substitute x. Now this becomes a quadratic equation. Now quadratic equations are solved using the quadratic formula. So now using the quadratic formula, we can actually see that x can be found using this formula. So x is equal to that, and then when we simplify this, we are left with that value. So now x has two different answers. So x can be 12 over 20, or x can also be 10 over 20. Simplify that. 12 over 20 is 0.6, and 10 over 20 is a half, which is 0.5. So that means cos theta is either 0.6 or cos theta can be 0.5. Now for cos theta being equal to 0.6, this is what we have. So we can actually see that z, so substituting it in the formula that we are given, z power n plus z negative n being equal to 2 cos n theta. So when you substitute in the value of cos theta, so you can actually see that this is what we have. So z power 1 plus z negative 1 becomes that. So we have z plus 1 over z is equal to 6 over 5. So when we cross multiply, we're left with 5z squared plus 5 is equal to 6z. So now we can apply, so we end up with this. So this is another quadratic equation. So we can apply quadratic formula again to find the value of z. So after quadratic formula, we can actually see that we end up with that. So now we are left with a root of negative 64. That means there's going to be an I value somewhere. Then this is what we actually have. And then you can actually see that this becomes 6 plus or minus 8i over 10. Simplify this and we have 3 over 5 plus or minus 4i over 5. And now those are two values of z, the first two values of z that we're actually looking for. So z can be 3 over 5 plus 4i over 5, or 3 over 5 minus 4i over 5. So this is actually a combination of two different answers. Alright, how about for cos theta is equal to 0.5? Now we know that this, we're going to substitute it into the formula, and this is what we end up having. Alright. Now this is what we end up having. So now we know that z plus 1 over z is equal to 1, because 2 times 0.5 is 1. So we can actually say this is what we end up having. And then now we have a quadratic equation. So we're going to apply quadratic formula again. So having applied the quadratic formula, we are left with this. And then we know that this can either be 1 over 2 plus root 3i over 2, or 1 over 2 minus root 3i over 2. So basically, those are the 4 different answers that we get. So those are the values of z. Alright, so let's move into another section of De-Moivre's theorem. So now we're going to find how to find roots of complex numbers of higher degrees using our knowledge of De-Moivre's theorem. Now we've already used a formula before of how to find the square roots of different numbers, but now we're going to use De-Moivre's theorem to find those square roots of complex numbers that even go beyond the basic square roots. So if you're being asked to find the 4th root, the 5th root, the 6th, it doesn't matter, anything higher. So this is where it's going to become useful. Now this formula here can also find the basic square roots, so it can also be useful for that. But in addition to that, it can also find any other higher values or roots of higher degrees. So when we want to find the root of complex numbers by making use of De-Moivre's theorem, we use that. So we know that z, so z 1 over n, that's like a square root, a root of something, is equal to that. So from De-Moivre's theorem, so when we bring the 1 over n in, it can actually be expressed like that. So now here's the general format that we usually use. So but for the general form, this is the formula: z is equal to r bracket cos 360 cos bracket 360k plus theta plus I brackets 3 sine I sine bracket 360k plus theta. So that's what we basically use. So now if we use that basic format and we substitute these other values in, so when we put these in and compare, we can actually say that this becomes our final formula. So now this is the formula that you need to memorize, and this is the formula that we're going to be using to find the different roots of different numbers. So now this is true where r and theta, r is modulus and theta is argument of the complex number respectively, where we have k is 1, 2, 3 continuous up to n minus 1, and n is the integers. Now this is going to make making a lot of sense when you look at different examples. So question number 1, we're being asked to find the cube root of z is equal to 1 plus I root 3 to 1 decimal place. So how do we solve this? So now the square root, the cube root can be stated this way. Cube root is like z to the power 1 over 3, which is equal to, which means on the other side we have 1 plus I root 3 to the power 1 over 3. And basically, because we are being asked to find the cube root, remember that the n value, of course this is z power 1 over n, we can actually see that the n value is going to be equal to 3. So it's important to note what the n value is. So the first thing we're going to do is we're going to find modulus. So we're going to first deal with this. So we're going to assume that 1 plus I over root 3 is equal to z. So when you find the modulus of that is going to be equal to this, which means we're going to have root 4. Of course, root 4 means 2. And then if we're to find the argument, we can actually say that we're dealing with the first quadrant, of which to find the argument of a value in the first quadrant where the real part and the imaginary part are positive, we end up having tan inverse of root 3 over 1, and the answer to that is 60 degrees. So from the general formula of finding the root of a number, we know this is the general formula. Then let's substitute in the values. Alright, so therefore now we can substitute it into the equation. So as you can see, where there is z, we can put in 1 as 1 over 3, which represents the cube root, and then we can actually see that now we found the r as 2, so we have 2 to the power 1 over 3, and then inside the brackets we can actually see that where there is theta, we substitute it and put the 60 degrees. So this is what we end up with. And now because we are dealing with cube root, it means the values of k only go from 0 up to 2, because remember that the last value of k is equal to n minus 1, and now because we have n being 3, so that means the last value of k is 3 minus 1, which is 2. So that's how we have k values only ranging from 0 to 2. So we have 0, 1 and 2. Alright, so now we're going to look at the case when k is 0 to find the first value of the cube root. So in substituting the values there, we know that we're going to end up with cos 20 plus I sin 20. And then these are going to be the values. So 2 to the cube root of 2 is going to be equal to 1.2599, and then cos 20 is 0.9397, and then sin 20 is 0.3420. Alright, so now when we multiply everything by the value outside, this is what we end up with. And now because the question asked for us to put 1 decimal place, this is what we end up having, and this is going to be the first value of the cube root. So let's look at for the second value. Now remember, a cube root has 3 different answers, and that's what we're going to do. So now let's find the second answer. So now substituting in the values of k being 1, we end up with that. So we know that now we'll have 420 divided by 3 on both sides, and then we know 420 divided by 3 is 140. That's what we have. And of course 2 to the power 1 over 3 is 1.2599. But cos of 140 is a negative, so we have negative 0.7660, and sine of 140 is actually a positive, which is 0.6427. Alright, and then we are left with that when we multiply in the brackets. And to 1 decimal place, this is what we end up having. How about when k is 2? When k is 2, we can substitute in the value of k in, and then we end up having 780 divided by 3 on both sides. And then what we know is 780 divided by 3 is 260, so we end up having that. Now the cos of 260 is a negative 0.1736, and also the sine of 260 is a negative, which is a negative 0.9848. So multiplying inside the brackets, we end up having that value. Then to 1 decimal place, this is what we end up having. So hence the roots of z, hence the cube root of z, which 1 plus I root 3 is. So the answers are 1.2 plus 0.4i, 1.0 plus 0.8i, and negative 0.2 minus 1.2i. So let's look at a question from UNEB 2008. We're being asked to find the fourth root of z is equal to 4 plus 3i. So now this is what we are finding. So we're dealing with fourth root, which is 1 over 4, z power 1 over 4. And now our n value is going to be equal to 4. That means our k values shall range from 0 to 3, because the last value of k should be equal to n minus 1, which is 4 minus 1, which is equal to 3. So it's 0 to 3. So finding modulus, you can see that the modulus of this is that. So we're going to have root 25, which is equal to 5. So find the argument. Now you can see that both the real and the imaginary side are positive, so we're dealing with the first quadrant of the Argand diagram. So the argument of this can be found using tan inverse of 3 over 4, of which that is equal to 36.7 degrees. So from the general formula, this is the general formula for finding root of any equation in complex numbers. Using De-Moivre'S theorem, you can see that this is what we have. So the k values range from 0 to 3. Now this is what we end up having. So when k is 0, we substitute in the values, and you can see that r, of course, is 5, because that means we'll have 5. We have to find the fourth root of 5. Then we can see when we substitute in the values, this is what we end up having. And then 4th root of 5 is 1.4953. So when we multiply to the values in brackets, this is what we end up having. Since the number of decimal places were not specified, we can actually leave it to 4 decimal places. So that's when k is 0. So when k is 1, this is what we end up having. And then we can see that this is what we have. And then multiply that into bracket, and we have negative 0.2385 plus 1.4762i. When k is 2, this is what we have. And then substituting the values, we end up having negative 1.4761 minus 0.2385i. And then when k is 3, we're going to substitute in the values. We can actually see that this is what we end up having. Then the answer becomes 0.2385 minus 1.4761. So therefore, the 4th root of 4 plus 3i, the answers are 1.4761 plus 0.2395i, or negative 0.2385 plus 1.4762i, or negative 1.4761 minus 0.2385i, or 0.2385 minus 1.4761. So obviously the 4th root of a number generally must have 4 different answers. And that, alright, so let's move on to another number. So this is question number 3. So being asked to evaluate this. So being told that bracket 1 plus I root 3 to the power 2 over 3. Now this is slightly different. Now this one we'll have to first simplify because we cannot find the root directly. So how do we do this? So you can see that this can be expressed in this format, because you can see that the power is the same as 2 times 1 over 3. So we have a part of it which is actually squared. So now from the inside, we're going to square the brackets. So when you square those brackets, we can actually see that this is what we end up having. So it becomes 1 plus 2i root 3 plus bracket I root 3 squared. Alright, then when we simplify this, now this is an example where we actually have to simplify. We can see that I squared is actually negative 1 and root 3 is equal to 3. So that's why we're left with a negative 3. Then 1 minus 3 is negative 2 plus 2i root 3 to the power 1 over 3. So now this has been simplified. So now basically, we're now going to have find the cube root of this. So now that's how it becomes. So now this is going to be easy. Alright, so now we're going to let z be equal to that. And then we can actually now see that the value of n is going to be equal to 3. So to find modulus, we're going to find the modulus of this. And then the modulus is going to be root 16. And then, of course, the answer is equal to 4. Right, now moving on, we're going to find the argument. And then the argument, we can actually now see that this value here resides in the region of the quadrant where we have a negative real and a positive imaginary. Now that means we are dealing with the second quadrant. So in the second quadrant, remember that we use the formula 180 degrees minus tan inverse of whatever value that we actually get. So we're going to have the imaginary over the real, over the negative real. But because remember, because of these bars, we're not going to consider the negative value from here. So this is what we end up having. So we end up having 180 degrees, and this value here, tan inverse of this, gives us 60 degrees. 180 minus 60 is 120. So we end up having 120 as the argument. So from the general formula of finding root of a complex number, we can actually that this is what we have. So we're going to substitute in the values. So we're dealing with the cube root. So we're going to substitute in the values and the value of argument. And now because we're dealing with cube root, it means the values of k range from 0 to 2. Because the last value of k must be equal to n minus 1, which is 3 minus 1, which is 2. And that's why we have k values from 0 to 2. So when k is 0, let's substitute that in. When k is 0, this is what we end up having. We end up having that. Now the value of 4 is, the value of r is 4, and that's what we have. So we have cos 40, I sin 40. And now when we put those in decimal values, this is what we have. And then open brackets, and that's what we end up having. So how about when k is 1? When k is 1, we're going to substitute the value of k as 1, and that's what we have. So I'm left with 4, cube root of 4 into cos 160 sin 160. That's what I end up having. Now you can see that cos of 160 is a negative and sine of 160 is a positive. Now open brackets and we are left with negative 1.4917 plus 0.5429i. How about when k is 2? When k is 2, this is what you end up having. Substituting the value of k as 2, then you can actually see that we'll have cos 280 and sine 280. Now the sine of 280 is a negative, so that's why we have a negative value there. So when you open brackets, we're left with 0.2756 plus 1.5633i. So hence, the general value that would be given, hence the answer to this is either 1.2159 plus 1.0204i or negative 1.4917 plus 0.5429i or 0.2756 plus 1.5633i. Alright, so that's it. Now let's look at some trial numbers. Now these are trial numbers you can try out in your free time to get better at whatever I've taught in this portion of De-Moivre'S Theorem. Now practicing them will help you get a better understanding and perfect it thoroughly. Thank you so much for watching. Thank you so much for watching this video. Thank you for watching to the very end. I am very grateful. I hope this video has blessed you and that it has improved your knowledge of complex numbers. If you really enjoyed this video or if it really helped you, feel free to leave a like on the video. And then if you're new to this channel, I encourage you to join our community by clicking on the subscribe button and then joining it, and then make sure to hit the notification bell so that every single time I upload a new video, you'll get updates on your notifications. See you in my next video.